Molecules typically exhibit pure rotational state transitions in the microwave region of the electromagnetic spectrum. Now, we can model these rotational transitions by using the rigid rotor model, and so remind you that the energy levels for the rigid rotor are equal to h bar squared over 2I times j plus 1. Now, as we've noted, when we talk about spectroscopy, we often use a specialized set of units that relate to either the wavelength or the wave number, or something like that. So, in fact, what we'll be doing is modifying this a little bit to divide by Planck's constant times the speed of light, in which case we're going to end up writing this in terms of a rotational constant, b tilde times j plus 1. And now this b tilde is going to be something in units of wave numbers or inverse centimeters. Now, if you compare this equation to this equation, it gives us a way to express b in terms of the moment of inertia of the molecule. So in other words, when we divide this equation over here by hc, the stuff that happens, the stuff that is in front of the j times j plus 1 is going to be equivalent to b tilde. So that means h bar squared over 2I hc. All right, so this is going to be our way of connecting things that we measure spectroscopically, which will be in terms of this rotation constant, we'll be able to connect this ultimately to the moment of inertia of the molecule, which will give us some idea about the physical characteristics of the molecule. Now, I'll note that for many molecules, especially diatomics, we're going to find that this rotational constant is typically less than about 20 inverse centimeters. Oftentimes for very large, massive ones, so I'm talking about things like I2 or BR2, we're going to have rotational constants that are in fact less than 1, in fact much less than 1. So these rotational constants, they're always greater than 0, okay, they have to be, and they're typically going to be less than 20 wave numbers. All right, so we've seen that the selection rules tell us that that the change, selection rules, the change in J for an allowed transition must be plus or minus 1. So let's look first at J, delta J equals plus 1, because that's going to equal absorption. In other words, we are increasing the energy to increase J by 1, so we're going from J, our initial J, to the next higher J. All right, so what is the change in energy that occurs when we make that? Okay, if we use our rigid rotor energy levels, we'll end up with E sub J plus 1, our final energy state, minus our initial energy state. So when we write this out, it'll be beta, and this is implicitly all over HC. It'll be our B tilde times J plus 1, and then J plus 1 would be J plus 2 minus B tilde times J plus 1. Now notice that both of these terms are dependent upon B and on J plus 1, so we can factor that out. And then what's left is J plus 2 minus J. Well, J plus 2 minus J is just 2. So our final result here is that the change in energy when we make this transition is actually just proportional to J plus 1. Now, what this means, in effect, is that if we were to tally up several consecutive energy changes, and so let's do that. So I'm going to write this as follows. Delta E of the final state, so let's say the final state is 1 and the initial state is 0. This is the way we'll write that transition. We're going from the J equals 0 to the J equals 1 state. Well, the J that appears in here is the initial J, the way we have formulated this. So when I plug in J equals 0, that's just going to be 2 times B tilde. If I looked at the energy change from 1 to 2, remember it can only change by 1. All right, then my initial J is 1. When I plug 1 in here, I'll have 1 plus 1 is 2 times 2, or 4 B tilde. when I look at the change in energy from 2 to 3, and I realize this seems like it's dudley dull going up one at a time, but when I change J to 2, this will be 3 times 2, or 6 B tilde. So this is the gap between successive energy levels. But the thing I want you to notice here is this gap consistently varies by a gap of 2 beta. So what does this mean? This means that the successive energy levels, or I should say successive transitions, are equally spaced. And they're equally spaced by this amount that is proportional directly to B tilde. So this means if we look at a spectrum and we see a bunch of lines that have equal spacing between them, the gap between the lines is something that we can relate to this rotational constant. So by measuring the spectrum and looking at this gap between the lines, we can determine a value for B tilde. And once we have a value for B tilde, we can now come up here to our expression for B tilde in terms of other constants, and h bar squared and h and c are all known. This allows us to then get the moment of inertia for the molecule. All right, we can also do this for emission spectra. So in the case of emission, we must have delta J equal -1. So we're basically going from an initial state J to a state J minus 1. Now, since we're declining in energy, I'm going to write this a little bit different. I'm going to write this as delta E of 1 going down to 0. All right, so this is the emission spectrum here. So when we look at this type of energy transition, it turns out that the delta E that we calculated above, and I'm going to let you work through this exercise, but you can show that this delta E for this emission now is not going to be equal to 2B J plus 1. It's going to be equal to just 2B times J. So now when I go from 0 to 1, again, this is my initial J. So when I calculate this, this first one will be at 2B tilde. E2 to 1 will be at 2 times 2, or 4B tilde. And 3 to 2 will be 2 times 3, or 6B tilde. So you can see the same pattern is emerging, that these successive differences here are all going to be the same amount. And so it doesn't matter whether we're looking at absorption spectra or emission spectra, we should be able to measure our rotational constant simply by looking at the spacing between the lines. Now, I've drawn attention to the fact that B tilde is equal to h bar squared over 2IHC. Okay, I've got h in the numerator and h in the denominator. If we straighten this out, it's going to simply be h bar over 4 pi, because h bar is h over 2 pi, and I've now canceled the h out of here, times c times the moment of inertia. But I can write the moment of inertia as m sub r0 squared. Sorry, mu times r0 squared. Mu in this case is the reduced mass for the molecule. So I can easily determine its value if I know the molecule. So now what happens is I'm able to find what is the equilibrium bond length for this diatomic molecule. If I were to take this expression and solve for R0, what I would get is the following. I would have h bar over 4 pi c mu times our wave number rotational constant, and then I'm going to take the square root of this whole thing. So this now basically allows us to take these pure rotational spectra and get direct information about the bond length, for example, of a diatomic molecule.